rooted in optimization, trying to use annealers for these sorts of problems. But despite this historical interest, there's always sort of been this historical problem lurking. To see what that is, we'll consider the general idea of quantum optimization. And in fact, the very basic prerequisite is that you have to make the quantum system feel the problem you're trying to solve in some way. You need to compute the cost function on the quantum computer. And what this usually means is that we need to do queries to the cost function to phase computational basis states. And whether you're doing Grover's, search, annealing, population transfer, or QAOA, you're doing something like this. And quantum annealers, their downfall is that they could only realize easily solvable cost functions due to the physical restrictions of the hardware. But recent gate model experiments have also sort of fallen into this trap, limited to hardware native cost functions. And what do I mean by hardware native cost functions? That's when the problem graph matches the hardware topology. And what do I mean by problem graph? Well, we're gonna focus on discrete optimization of this particular form, the quadratic binary cost functions. This is sort of common in the QAOA literature. And all discrete optimization problems can in theory be mapped to this, potentially with some great overhead. But the two local structure means that we could visualize this cost function as a graph. And this historical problem is that people show performance of various optimizations where the cost function matches the hardware graph. So for example, in this study, our hardware grid looked like this, 23 qubits in a nice grid. But it should come as no surprise that problems of this form are not industrially relevant and easy to solve heuristically. So in this work, we studied random instances, both of these tailored hardware grid problems, but also prototypical computer science problem families, in particular, random instances of 3 regular max cut, as well as this fully connected Sherrington-Kirkpatrick model from the spin glass community. And as you might be aware, gate model quantum computers can get around the sort of physical restriction of the hardware topology by performing swap operations. And in particular, if we wanted to do 17 qubit fully connected phasing unitary, we could do it with this linear swap network, which actually only requires linear connectivity between the qubits. You basically bubble all of the logical qubits past each other. And if you do n rounds of this operation, each pair interacts once. So this is what it looks like for 17 qubits. And this purple box is this composite swap and phasing operation, which we can compile to gates that our hardware can actually do. Our 2-qubit entangling operation is this ISWAP-like green box, which we call the sycamore gate because it also has this conditional phase, but it serves as a stable compilation target where we could do anything we want. And in particular, we could do this composite operation with 3 applications of this gate. And as I sort of alluded to in the study, we're using the specific prescription of the quantum approximate optimization algorithm, which consists of repeated alternating applications of a problem unitary, UC, and a driver unitary, UB, which are single qubit X rotations and easy to implement in practice. Where again, the problem unitary phases states and encodes the problem you're trying to solve, and the driver unitary drives transitions between computational basis states. And this is a variational algorithm. Each layer has 2 parameters, sometimes called angles, gamma and beta. Gamma parameterizes the problem unitary, beta parameterizing the driver unitary. And we could hook this up to a classical outer loop optimizer to suggest new parameters to improve the quality of our solutions, which here we'll typify by the expected value of the cost function, which we're trying to maximize. And first, we restrict ourselves to the shallowest depth version of this algorithm, where we set this depth hyperparameter p equal to 1. So there's only 2 angles, and we could plot the quality of solution versus the 2 parameters and do an exhaustive search. So this is the parameter landscape for a 23 qubit hardware grid problem with random plus or minus 1 weight couplings on all of the edges, with a noiseless simulation plotted on the left and our experimental results on the right. And you could clearly see that performance is quite good, even at this relatively large problem size of 23 qubits. All of the hills and valleys are in the right place. There's the contrast is quite good, and everything looks like it's operating nice. And in fact, a classical loop optimizer initialized from this sort of red square follows this red trace and can quickly find maximum, whose theoretical position is shown on the left with a blue star, and then the classically, the variationally determined final point with a circle on the right. And this kind of really nice result is possible thanks to good hardware, in particular, no crosstalk. And I should mention that there's a developing tradition of presenting these QAOA parameter landscapes as a really nice visual indication of what's going on in the quantum system. I really like that. I think some of this heuristic and holistic benchmarking, it can be really useful. In the previous sort of best parameter landscape was presented at n equals 20 for a sort of hardware native problem. But like I said, hardware native problems aren't typically of industrial relevance. So we can also show the p equals 1 landscape for the much more complicated and difficult to implement Sherrington-Kirkpatrick model, which again is this fully connected graph with random weights. Here we show at a more modest size of 11 bits. And you could see that the hills and valleys aren't as sharp as before, but they're all still there and they're in the correct place. And our classical outer loop optimizer is still able to climb uphill and find optimal parameters quickly. This is sort of best in class performance for very deep circuit. As far as I could tell, the previous demonstration of one of these landscapes on a complete graph was recently published at n equals 4. So this is significantly more complex, and we're still able to extract a meaningful signal from this. Now, if you'll bear with my color scheme for a brief moment, we're going to move to a regime where we compute the optimal angles classically and find them theoretically, just so that we could do more of these problems. We compare the performance of many random instances at a variety of problem sizes and circuit depths. So we choose 10 random instances for each number of qubit n and each hyperparameter p. And here we show the performance of our device on the hardware grid problem up to a maximum of 23 qubits. The upper band of square points is the theoretical noiseless value, and the lower band of circular points is the experimentally determined. And again, we're showing the quality of solutions where higher is better. And you can see there's an interesting feature. After about 10 qubits, the performance normalized in this way levels out. This is sort of expected from the simple compilation and the low degree of the graph if you assume a local error model. So we have good evidence that we're not being completely destroyed by crosstalk here. There's a different story when you start looking at the fully connected Sherrington-Kirkpatrick model. While even at this relatively deep circuit, we're showing numeric or experimental data at p equals 3, which requires over 1,200 2-qubit gates for the largest 17 qubit problem. You could see that there's still significant performance in 10 to 16 qubit range, but there's clearly this degradation of performance as you increase in problem size. This sort of should be a wake-up call that it may be difficult to scale QAOA compiled to an actual device up to problem sizes which are industrially relevant. We can also pivot what we're plotting and look at how things change versus this depth hyperparameter P. And without noise, higher P is always better. That's the green curve. It's monotonically increasing. But the presence of noise makes it a trade-off. So we show the average experimental quality versus P, where this mean peaks at P equals 3. And perhaps a more informative way of looking at this experimental data is instead of averaging all of these instances, for every instance, and again, there's sort of 10 instances from problem sizes from n equals 10 to n equals 23, figure out which hyperparameter value of P maximizes performance, and then we plot that histogram inset in this plot. And we find that over half of our problems on the hardware grid have maximal performance at P equals 3. And this is really nice to see, because if you look at the previous experimental demonstrations of QAOA, the sort of previous best in class was showing that you could match the performance of P equals 1 with a P equals 2 circuit. But here we're actually seeing the ability to dial up the quality of solutions by going to higher depths. And in summary, we were able to implement the QAOA on our new processors. We showed qualitative agreement between these landscape plots, both on easy to compile hardware grid instance and more challenging and more realistic fully connected models. The quality of our device permitted classical optimization of this variational algorithm to effectively find variational parameters. And we show that hardware native problems show some desirable features. There's sort of n-independent noise that permits good performance at large sizes. And the simple compilation means that we could go to greater depth to improve the quality of solutions. However, this demonstrates that real problems require more compilation, which leads to challenges in scaling up. And I mentioned there's an emerging tradition of using QAOA as a holistic application-specific benchmark for quantum devices. And I think this is a really promising avenue, along with other more principled QCVV techniques. But we'd love to see some more non-native graphs being solved in these. And thank you for your attention. And I'd also like to thank the entire Google Quantum group for building this hardware and supporting this project. This was really a team effort. And I'm happy to take questions from Slack.
Thank you very much, Matt, for this very interesting talk. As a reminder, please post your questions in the appropriate Slack channel, which is session 11, Talk to Harrigan. So we start with a question from Brendan Wright. He's asking, with respect to annealers only being able to implement easy to solve, quote unquote, cost functions, how are you defining easy to solve? And then he says that there are NP hard problems that have real world applications that can be implemented on the chimera graph for annealers. For example, verification and validation or fault diagnosis problems.
Yeah, easy to solve, meaning that we've sort of showed that heuristics can perform pretty well. And maybe I'm sort of out of date on the latest with annealers solving NP hard problems, but I think it's safe to say the sort of promise from the early 2000s has not really been borne out with them because of the difficulty of compiling things to the chimera graph.
Thanks. Next question is by Elias Combaro. I hope I said that well. He's asking, what classical optimizers do you use?
Yeah, so we use a new optimizer that should be hitting the archive in the next month or so. And the details will be in the paper, which should be coming out very, very shortly on this work. We call it model gradient descent. It's a surrogate-based model where we adaptively learn a quadratic fit to the energy landscape, which allows us to smooth over a lot of the stochasticity of the objective function.
Thanks. Next question by Peter Morgan. He's asking whether you can give some more examples of non-native graphs.
Oh, I'm not sure I understand the question. A non-native graph is anything that requires a swap to be in the quantum circuit. So we have our hardware topology is this 2D grid. Most superconducting architectures are planar grids of qubits. So anything that isn't a planar graph of problem bits connected to each other would be a sort of non-native graph. And then even if you look at the ion trap experiments, they have this long range problem that they're solving, but it's still native to the interaction of the actual trap setup. So for example, if you wanted to do like traveling salesman problem or something, you'd map that to a quadratic binary optimization problem, and it would not be on a grid. It would have a topology that would in general not match your hardware platform.
So related to this, Alex Kissinger is asking, do you think that bad scaling behavior for non-hardware native graphs can be fixed by a good routing strategy? Or is it inevitable?
That's a good question. In the paper, we also do problems of 3 regular max cut, which instead of doing this linear swap network, we use a routing algorithm, and there's probably some room to improve that performance just because based on the routing algorithm we actually used. But this can only buy you so much. In particular, for the data shown on the Sherrington-Kirkpatrick model, the swap network we use is optimal. You sort of can't do better than that, just from a basic counting argument.
Can I ask you, what are you computing in the Sherrington-Kirkpatrick model? Is it the partition function or?
So we're trying to find the ground state perhaps, but we're plotting sort of the average value of the of this cost function, which is on this graph.
Right. Okay, so there's a couple more questions in Slack, if you'd be so kind to answer them there.
Sure.
And this will conclude this afternoon session. Please reconnect in 20 minutes at 40 past 5. Sorry, yeah, 40 past 5 UK time for the last session of the talk. Thank you.